This conference will now be recorded.
Okay, awesome. So yeah, so let's get started. So just going over yesterday's class. So let's just have a quick recap of what we have discussed. What are the different topics that we were handling in the yesterday's class. So I think in the yesterday's class we started off with boosting, if I'm not wrong, right? So we basically went on to first compare how is a boosted decision trees better over the other kind of models that we've been discussing, right? So we started off with a comparison between how does decision tree perform versus how does the bagging algorithm works versus how does random forest works, and then we went on to something called as boosted decision trees, correct? And under the boosted decision trees, what we did was we was what we did was we were basically discussing about an algorithm called AdaBoost, and we saw its implementation also here in Python, correct? And then what we did was we jumped into this neural network, right? More specifically, we started our discussion about multi-layer perceptron, correct? I'm going to give you all a quick recap of what we've discussed in yesterday's session, but kind of defining the agenda for today's class before that. So we started off a discussion of multi-layer perceptron. We spoke about perceptron, etc. How can we probably use it in the creation of a linear regression or a logistic regression algorithm, right? And for today's class, what we're probably going to do is we're going to jump into the more specifics about the multi-layer perceptron. More specifically speaking about how does a model get created, what kind of an architecture should I probably keep to solve a particular problem, how can I design a particular network. So the reason is because neural network is once again another black box model like what we have, okay, the boosted decision trees and all. So unless you design it properly, you don't get the predictive parts, in a very good, outcome, I would say, as a very good outcome. So designing and understanding the architecture of a neural network, why do we do so? Why do we not do the other way? So getting into all of those intricate details is very important in a multi-layer perceptron. I think that is going to be the agenda for today's class. And then we're going to move on to convolutional neural network, okay? And we'll start looking at certain use cases also where we try to implement multi-layer perceptron and convolutional neural networks, okay? So this is going to be the agenda. So let's quickly have a recap of yesterday's session, which is basically the multi-layer perceptron that we started our discussion with, okay? So I think we were here, just give me a second. Sorry guys, just give me 1 second. I need to check which OneNote are we following. Yeah, I think it was here. Okay. Sorry guys, I think it has not synced, so I think we've probably lost those pages. Just give me 1 minute.
This conference will now be recorded.
Great. So yesterday's class we started off a discussion with something called as multi-layer perceptron, right? So what is a multi-layer perceptron? Basically, we started off a discussion about something called as a perceptron, where we understand that the perceptron is more like the fundamental unit of your entire neural network here. Guys, just give me one more second. I need to make another spot setting change. Yeah, now we are good. Okay. So we start off a discussion by understanding that we have something called as a perceptron, which is the most fundamental unit in our neural network here, right? And what happens to the perceptron is that it's going to receive an input, basically your predictors, and it is going to have a sort of a weight, to this particular condition. It's going to have a small parameter, or what is something called as a weight. There is also another input that it is going to receive, something called as bias. And then we are saying, hey, there is an output that we are able to calculate, which is y cap is equal to input into weights plus bias, which is actually speaking, if you all remember, it's going to resemble like how our linear regression model was working. It's merely just a linear combinations of variables, that's all. Beta naught plus beta 1 times of x, correct? And then we later on went on to understand that there is also something called as an activation block, which is available here. Using this particular activation function, you can make the output to become nonlinear also if it is required. Else you may just keep it as it is. You may keep it as something called as identity, right? Identity. So what happens is you get it as a linear outcome itself as it is. But rather, if you keep some other function, it can become a non-linear outcome, correct? So we understood that this perceptron that we are talking about, right, is the fundamental unit of your entire neural networks here, right? So this is the fundamental unit of your entire neural networks. So this one single guy, as we discussed yesterday, is very powerful, and it is pretty much equivalent to how a linear regression model might work. Because you can see it is basically beta naught plus beta 1 times of x, right? And what was the next point of a discussion? We went on with a discussion about something called as a multi-layer perceptron, where we said, hey, even if a single perceptron is an enough predictive model, why don't we just imagine by keeping a lot of perceptrons in a single, series kind of a connection, where this guy will probably become our layer 1, this guy can become our layer 2, he'll become our layer 3, and he will more or less become like your output layer. So we're basically saying, hey, if a single perceptron himself is a very powerful predictive model, why don't we just imagine creating a lot of such perceptrons, which is equivalent to coming up with a lot of such predictive models? It's more like the ensemble of models that we discussed previously, right? Where we are combining the predictive power of a many predictive models, the same thing. We are trying to combine the predictive capability of a lot of perceptrons here. And as I told you all yesterday, you can just go back and increase the number of perceptrons in a single layer also. It need not just be stacking a lot of layers, but inside a particular layer also, we can go back and stack a lot of such perceptrons, right? So this is exactly what we kind of discussed yesterday. It was a pretty, crisp recap that I just gave you, but we dealt in more amount of details is what I understand, right? So perceptron, the fundamental unit, the moment you start stacking them, it becomes something called as multi-layer perceptron here. And then we went on to discuss, how we can probably solve a linear regression model or a logistic regression model using what? Using this particular single perceptron that we just discussed here, right? So linear regression model, we said, we're using Keras to go back and implement it using a single perceptron here. Similarly, when we do a logistic regression, we went ahead and we kept a single perceptron, but with the activation function, something called a sigmoid, right? So what I'm going to do is, guys, I'm going to start a discussion with this multi-layer perceptron here, okay? So MLP is the next core concept that we're going to discuss in detail now. So whenever it comes to a multi-layer perceptron, guys, there are basically three different, I would say, properties or kind of characteristics that you need to be worried about. Okay, whenever it comes to a multi-layer perceptron, there are three characteristics, or let's say three properties that we should basically, kind of concentrate on when you're trying to create a powerful MLP model. The first property is what kind of a architecture are we designing here? Now, what is the architecture of the MLP that we are designing here? That is number one. Number two is what is the activation functions that we're using at each and every layer? Because what do we have? We have perceptrons at each and every layer, and every perceptron is having an option of having some sort of an activation function. So one is I need to decide what is architecture, which is how many layers, how many perceptrons I should keep. That is all okay. And the second thing that we need to be worried about is also the activation functions. At each perceptron, what is the activation function we should probably use? Should it be linear? Should it be non-linear? If it is non-linear, what are the different activation functions available? That is number two. Number three is basically the training algorithm. How are you probably training your multi-layer perceptron? So these are the three properties or characteristics of a multi-layer perceptron model that we need to probably concentrate on. So you need to know what kind of an architecture are we supposed to keep to solve a problem. Number two is what should be the activation functions at each and every layer. Number three is what kind of a training algorithm am I supposed to adopt to solve this particular multi-layer perceptron model here. Okay. So let's talk about architecture. What exactly do you mean by architecture? As I told you all, we need to think about how many layers of perceptron should I probably keep. Number two is at each layer, right? So at each layer, we need to understand how many perceptrons should basically get stacked. Both the things are very important. At each layer, I need to understand how many perceptrons should I probably stack and how many such layers should I probably have to solve this particular problem here, correct? So what is a multi-layer perceptron? As I told you all, you're basically stacking a lot of perceptrons one above the other. You're stacking a lot of layers. That is what is multi-layer perceptron. So it goes like this. So what we are going to do is we're going to quickly try to create a diagram of a multi-layer perceptron. So let me create my first layer here. So this is the first layer we are creating. Okay. So let us probably add 6 perceptrons here. 1, 2, 3, 4, 5, and 6. So we have 6 perceptrons right now. Now what we're going to do is we're going to have some input set of features. We'll pass it as an input to all the 6 people here. So the input is getting shared with all the 6 perceptrons that we have here. Okay. So what will you have? You will have weight 1, you will have weight 2, you have another weight, your weight 4, weight 5, and weight 6. What will happen? Each of these guys will give you their outputs: y1, y2, y3, y4, y5, and y6. So there are 6 outcomes coming from the first layer. Now what we will do is we'll probably create another layer here. Okay. I'll probably just assume 4 perceptrons: 1, 2, 3, and 4. So this guy says, hey, I will share my outcome with all the 4 perceptrons at the next layer. Okay. Similarly, the next guy says, even I will share all my outcomes with the 4 perceptrons here. Similarly, the third guy says, hey, I will share my outcome with all the perceptrons. In the same fashion, everybody will start sharing their outcomes with all the 4 perceptrons available here. So what will you have? You have 6 perceptrons here and 4 perceptrons here. 6 into 4 is what? 6, 12, 18, 24. 24 different connections is what we will have. Or 24 different weights is what we are supposed to have. Agree or not? Because every connection should have a weight. So this guy will become a W7, he will become a W8, W9, W10. So every perceptron is having 4. So 6 4s are what? Basically 24 connections, which means 24 weights is what I will have. Similarly, what will we do? We'll go back and create probably another layer. Okay, let me call this as the final layer here. I'll probably have, let's say, 2 perceptrons right now. So these guys will share their outcomes with all the 2 perceptrons here. So how many connections you have? 4 and here 2, which means you'll have 8 connections with us, which means 8 weights are required here. Then now what you'll get is you'll get 2 outputs. This is output 1, you get output 2. Why are we getting 2 outputs? I'll come back in a minute and I'll tell you all. So for now, if you all look at it, this is a multi-layer perceptron that we have just designed, isn't it? So what are we saying? We are saying, hey, there are certain inputs I would like to share with everybody. So there are 6 perceptrons here. They are getting connected by 6 weights here. Then these 6 people, they will compute some outputs which will be shared with another 4 people here. The output from these 4 people will be shared to another 2 people. These 2 guys will give you output 1 and output 2 here. So this is exactly how we have basically created our multi-layer perceptron. If you actually try to get into this particular max, right? So what is actually happening is, so your input data set is basically what? It'll have a certain number of data points, which becomes the number of rows, into how many columns will it have? It will basically have the number of features or the number of variables. Guys, I feel like I'm going a little fast. I'll just try to, slow it down. Now see here, this is our input, okay? So our input is basically going to be what? It's going to be a data set, right? So somebody will basically share as a data set. The data set is basically the input. So what will be the dimensions of our input? It will have the number of rows, which is nothing but the number of data points, and it will have a number of columns, which is equal to the number of variables shared with us. Say for an example, somebody is giving us 150 rows of data and they're giving us 5 predictor variables. So it will be 150 into 5, right? This is going to be the dimensions here, correct? Now what are we doing? We are coming up with a weight matrix. What is a weight matrix? Let's go back and check here, guys. The weight matrix will basically tell us that there are 6 weights required for the 6 connections he is having here. How are we having 6 weights here? Because we are having 6 perceptrons here, isn't it? It is because I have 6 perceptrons. Everybody should receive the input. The input won't pass as it is. Everybody should have a weight here. 6 weights because 6 perceptrons. That is why we are going back and saying, hey, the weights here should be nothing but the number of features times the number of perceptrons that you had in hidden layer 1. So by the way, this layer, right, we don't just call it as a plain layer, we also call it as a hidden layer, okay? All these layers are typically called as hidden layers, and this guy is called as an input layer. Usually it is imaginary. We don't construct it in the Python code. It's an imaginary layer, the input layer. All the other layers are all hidden. This guy will be called as your output layer, okay? So except your input and the output layer, everybody is hidden. Okay, so the input is also an imaginary layer. In Python, we don't really do it. Okay, yesterday also while writing the code, we were directly introducing these layers. So we don't talk about the input layer. It's something that is naturally constructed. But I'm just saying, it's an imaginary layer available at the very first, area. So it's an input layer here. The last guy will serve as an output layer. Anybody in the middle is called as the hidden layer, which means this guy is our H1. So now we are saying, hey, my input is nothing but number of data points into number of features, because it is nothing but the number of rows and the number of columns, or the number of data points shared and the number of variables shared. My weight matrix will be number of features into number of perceptrons in the hidden layer 1. Why did I use this dimension saying number of features? Very simple, guys. What is our formula? Our formula is input into weights plus bias, isn't it? What is the formula we are using? The formula is input into weights plus bias. If the input is actually speaking a matrix, If the weight is also a matrix, two matrices can be multiplied. Let's assume the dimensions are A cross B and B cross C. The two matrices can be multiplied only if the number of columns in the first matrix is equal to the number of rows in the second matrix. So what should match? The number of columns in the first matrix should match the number of rows in the second matrix. Only if this condition is satisfied, you will end up with a matrix dimension which is A cross C. So what should I have? If I know that number of perceptrons in hidden layer 1 is going to be the number of columns or the individual weights, how many such rows should I have? I should have it equal to the number of features we have here. Only then what I can do is, I can multiply these two people. Only then I can do input into weights. So this guy and this guy, they're basically matching. After I multiply, the dimensions will be number of data points into number of perceptrons in hidden layer 1. So why did I keep the number of rows equal to this one? It's because of matrix multiplication rule here. Right? You're supposed to multiply only when this condition is satisfied. What happens to the bias? The bias is nothing. It's a single value, but it will be shared with all the perceptrons, right? So you're saying, hey, it's a constant value, okay? It's a single value. So it's a single row of value, which will be shared with everybody. That's why we are saying 1 into number of perceptrons in H1. Now let's do the computation, guys. My output, or otherwise, y cap is nothing but input into weights plus bias. So what will be the resultant dimension? Since these two people are matching, I can do the multiplication between them. The result is going to be the number of data points times the number of perceptrons in H1. So it's going to be the number of data points times the number of perceptrons in H1. Right? And then you go back and add it with a scalar, which is nothing but 1 cross the number of perceptrons into H1. Ideally, it will be the same thing. So what will be the final result after doing input into weights plus bias? The dimensions will basically be number of data points cross number of perceptrons in hidden layer 1. So this is going to be the output size after you do this kind of a computation here. So let me go back and tell you again, guys. Let me give you a quick recap. So we were talking about perceptrons yesterday, correct? What is a perceptron? The perceptron is a fundamental unit of a neural network. So he is basically a person who will receive an input, he'll receive a bias also. There is going to be a weighted connection, he'll give you an output. Output is nothing but input into weights plus bias. So basically, he can take up an input vector like this, and you will come up with coefficient vector, which is weight vector like this, another bias value like this. When you multiply, you finally get a single scalar like this. So we are talking about a single output here. Now what will happen if I start stacking a lot of perceptrons one after another or one above the other? You're basically giving birth to a particular kind of a model called multi-layer perceptron here. What do you mean by multi-layer perceptron? Basically, you're saying, let's go back and keep stacking a lot of perceptrons, which is otherwise, your models, one after another, or even one above another, to create a layer of perceptrons or even multiple layers of perceptrons, which might be a much more deadlier combination compared to a single perceptron that we've been dealing till date. Right? So we're saying, hey, I want to make it more complex, okay? Shall we start creating a lot of predictive models? Sure, why not? Stack a lot of predictive models in a single layer, go back and stack a lot of such layers, it will give you something called multi-layer perceptron. But what are the main points I need to be worried about when I'm creating an MLP? There are 3 things that you need to be worried about. The first one would be architecture, the second one would be activation function, the third one would be training algorithm. What do you mean by architecture? Okay, so how many layers should I have? How many perceptrons should I have? Right? Why do I need to keep something like this? Those are the questions you will ask. Activation function, same thing. In the perceptron, what value should I get? Based on the value I want to get, I will go back and keep a suitable function. Should it be a linear outcome? Should it be a non-linear outcome? Or should it be probability between 0 and 1? Depending upon whatever you will ask, I'll keep such kind of an activation function. How can I train the algorithm to make much more better and better? So you can use certain solvers, you can use certain optimizers, certain methodologies of solving it. So these are the three different parts that you need to be understanding or to be worried about when you're creating a multi-layer perceptron. We are discussing the first piece, where what happens in the architecture, what is actually the computation that's happening on the inside? How do I get my output? So what is this architecture actually doing? Connecting all the people and all, what is the computation they are doing? These are the questions you might ask me. There are basically two things you all need to understand in a training algorithm, okay? There are two cycles. The first cycle is called as feed forward propagate, okay? So whenever you're talking about a multi-layer perceptron model, there are two cycles that you need to keep in mind. The first cycle is feed forward propagate. The second cycle is basically a back propagate. What is a feed forward propagate? If you all remember, we discussed yesterday, right? So I've created my predictive model. I give him the input, I get my output. So passing the input and getting the output is feed forward propagate. Then realizing this particular output and comparing with the true value will give me the error. Now rectifying the model in such a fashion that it reduces the error is called as a back propagate. So what is a feed forward propagate? So you're basically saying, hey, let me assume some value of coefficients, okay? So using some weight value, some bias value, something that I've just assumed, I will go back and compute my output, which is input into weights plus bias. This output, I'll compare it with my true value, which will give me something called as an error. Now using this particular error, I will realize how bad my model is performing. Then I'll go back and tell my model, hey, I think the weights and biases are pretty bad. Why don't you keep changing it in such a fashion that the error becomes better and better? Same thing like what we did in linear regression, isn't it? In the Excel while we were solving, we assumed some value of beta naught and beta 1. Then we got some error value. Then we told Excel, hey, I think this is the guy who you need to try to minimize. You can change my beta naught and beta 1 is what we told him, correct? The same fashion we are doing it. We create the multi-layer perceptron. He will assume some value of weight and bias. And in the feed forward propagate, you predict something. You will get an output. That output and true value are compared to get an error value. Later on, what we do is we say, hey, this predictive model is having this much of error. So I need to rectify the weights and biases. So the first stage of predicting something and calculating error is called as feed forward propagate. While the second stage of saying that, hey, this is the error I have, so can you please go back and rectify yourself, is called as a back propagate. So what's a feed forward propagate, guys? So I'm passing my input in a forward direction. I get my output. That's called as feed forward propagate. What is the back propagate? I send my errors from the back towards the front and ask my weights and biases to get retrained. That is what is called as a back propagate. You have a feed forward propagate, you have a back propagate. Now we are asking this question, how does the feed forward propagate work? So let's go back and compute the output. So we have assumed a neural network here. We have constructed a multi-layer perceptron. We have an imaginary input layer, as I told you all, right? We are passing input, okay? So let us assume the input is a matrix like this, which is having 150 data points and 5 columns probably. So we are saying I have 5 variables, okay? Age, BMI, income, blah, blah, something. And I have 150 data points here, 150 consumers probably. So this is a data set I have. Now what are we doing? Okay, Let us pass the information to the first layer, shall we? Because I have 6 perceptrons, 6 of these guys are going to predict something. Okay. For them to basically predict, what is the formula? It is input into weights plus bias. So basically, if input is a matrix, W should also be a matrix, B should also be a matrix. If the input dimension is nothing but number of rows into number of features, which is otherwise number of data points into number of variables, the weight matrix, if I want to multiply with this guy, he should be like this. It should be number of features into number of perceptrons in H1. Why did I say it is number of perceptrons in H1? Because the weights in the first layer is decided by the number of perceptrons we have. So 6 perceptrons, that's why 6 weights. So we are saying number of features into number of perceptrons in H1. Then what is a bias? A bias is a single value shared by everybody, right? So usually it's a single value, or they can be different values also. So we are basically saying, hey, it'll be biases B1, B2, B3, B4, B5, B6. Mostly they are all equal. Okay, in Keras, I think they are all equal. It's usually equal. Okay, so we are basically saying, hey, it's a single value that you will basically compute mostly. But anyways, here let us call it as B1, B2, B3, B4, B5, B6. So it's a single row of bias value. So we are saying, hey, you'll have a single row, but 6 bias values, B1, B2, B3, B4, B5, B6, right? Which is nothing but the number of perceptrons in hidden layer 1. When you multiply these two people, input into weights, and add it with the bias, this is going to be the resultant dimensions, right? Now tell me guys, do you all agree till this particular point? Till here, why do we say that, you know, the output after the first layer of computation is going to be equal to this dimension, the number of data points into number of perceptrons in H1? Do you all agree? Were you all able to follow this particular piece, how the matrix multiplication is happening? I felt I was a little fast, that's why I wanted to give a recap and ask the question. So does everybody agree? Okay, perfect. Okay, so there's a question. Weight by features. Can you elaborate, please? Sorry, which one are you talking about, Yatinder?
See, you can hear me?
Yeah, I can hear you.
Oh, yeah. So you said weight, you know, it should be number of features time number of, you know, so I'm just wondering, like, it's written W1. So what W1 include? Like, do you assign weight to each feature, like the 5 features in this particular example you're talking about? Okay. So how does? Can you maybe elaborate on that?
I'll do that. So see here, you have, let's say, x1, x2, x3. And let us assume that you probably have 150 data points. So typically, how do you create a linear regression model? We go back and say, hey, y is equal to beta naught plus beta 1 times of x1 plus beta 2 times of x3 plus beta 3 times of x3, correct? So which means every variable here should basically get multiplied by, you know, beta 1, beta 2, beta 3, or otherwise in our case, it will become W1 x1 plus W2 x2 plus W3 x3, correct? So we're basically saying the weight matrix should be what? Number of features times the number of perceptrons we have, correct? So we are saying, I'll make it as a bigger matrix here, okay? So we're basically saying, hey, it is going to be W1, W2, and W3. Okay, why? Because we have 3 features here, right? X1, X2, X3. When you multiply, it should become W1, X1, W2, X2, W3, X3. So there should be basically 3 weights here. And you need to have what? You need to have it for all the perceptrons that we see, right? So basically, it will become another W1, W2, W3, and we'll go on up to this particular case. So we need it for the number of number of features here because we have 3 variables here. All the 3 variables should take up a coefficient. That's why we are saying here it has to be equal to the number of variables that you put. Right. So when
Okay,
you
got
multiply,
it. Thank you. Yeah, got the picture. Thank you.
okay. So now when you multiply, you will have the first row of data. He will have x1, x2, x3. You will have w1, w2, w3. When you multiply, what will you end up with? w1 x1 plus w2 x2 plus w3 x3. This is what you'll end up with.
Thank you. Thank you.
Perfect. Okay. Yeah. So going back here. So we're saying, hey, if this kind of a matrix, if I try to keep and post I multiply, we're saying the output is going to be number of data points into number of perceptrons in H1. Let's go for another level. I want you all to tell me. We're talking about layer 2. So the input is going to be what? This guy, who is nothing but the number of data points I had originally in my data set times number of perceptrons in H1. Correct? Now can you all tell me what should be the weight matrix dimensions? So how can I define my weight matrix dimensions right now? So the weight matrix dimension should be equal to what? So just see, so this portion is what we want, right? The weights that we wanted. So we have 6 perceptrons here, we have 4 perceptrons here, right? And I told you that there are 24 weights here. So how did I say it's 24? How did you decide it? Okay. Very good answer, Sanjay, Yatendra. Good answers. Yes. So it should basically be what? You're saying it should be equal to number of perceptrons in hidden layer 1 into number of perceptrons in hidden layer 2, isn't it? So you can see here, I have 6 perceptrons here and 4 perceptrons here. 6 into 4, 24 weights is what I want. So now you're saying only if this number of columns is equal to number of rows, I can multiply. There itself you have an answer. So this should have been number of perceptrons in H1. And how many outputs you want when you multiply input into weights plus bias? You wanted only 4 outputs, which is equal to the number of perceptrons in hidden layer 2. That's why you can see we are saying it's equal to the number of perceptrons in hidden layer 2. Forget this piece. Let's forget this piece. Let's forget this piece also. So how did we come up with the dimension? Very simple. I have input. When I multiply it with weight and add it with bias, I need my outcomes. How many outcomes? I want 4 outcomes only. Why? Because there are basically 4 perceptrons with me. That is why we are saying, hey, the number of outcomes that I need right now is just 4 perceptrons. That's why we are saying number of perceptrons in hidden layer 2. But if I were to multiply, number of columns should be equal to number of rows. That's why we are keeping it's equal to number of perceptrons in hidden layer 1. Add it with the bias. Bias is going to be what? One row full of mostly equal numbers. I'll keep repeating, but sometimes some people will also keep different bias values, which is equal to number of perceptrons, once again equal to hidden layer 2. Now when we multiply, what will be the resultant outcome dimensions? Can you all tell me? When we multiply, what will be the outcome dimensions? Yes, guys, be a little bit more proactive. Yeah. So when we multiply, what will happen? Because these columns and these rows are matching, the output dimension should be this guy and this guy here, which should be number of data points, that is every row as it is, but represented against number of perceptrons in layer number 2. That is number of perceptrons in hidden layer number 2. This will be your output. Now it will keep going on and on and on. So next time what I can do is I'll just copy paste the same piece again. Okay, we'll just bring it down. I'll paste it here. Now we can just go back and say, okay, now we can just say, now it will be input will be the hidden layer 2, and here it should be 2, here it should be 3, here also it should be 3. The output will be what? Your number of columns equal to number of perceptrons in layer 3. Once again, I can just go back and copy the same piece. Let's just come down. We can paste it here. And once again, we can say, hey, the input right now is going to be what? Number of perceptrons of 3. Here it will be 4. Here also it will become 3. Here it will become 4. The output will once again be 4 perceptrons. So as you can see, guys, at every output layer, right? Well, let's start from input layer. See here. The input originally was the 150 rows and the number of features you gave, right? Then what has happened? It has become number of data points into number of perceptrons in H1. Then it became number of data points into perceptrons in H2. Then it became number of data points into perceptron in H3. Then later on it became number of data points into perceptron in H4. So the way you need to look at this is, guys, very simple. If I were to assume I had 150 rows and let's say 50 columns, let's assume we had 50 variables, okay? What a multi-layer perceptron is actually doing is, it's doing something called as dimensionality reduction. What is he actually doing? He's doing something called as dimensionality reduction. What do you mean by dimensionality reduction? Very simple, guys. Dimensionality reduction, or even before that, in data science, there is a popular concept of something called curse of dimensionality. So what do we have? We have something called curse of dimensionality. What do you mean by dimensionality? It's basically the number of variables. Okay. If there are too many number of variables, your models will basically become unstable. Or number 2 is, you may not even have enough computing power to create those predictive models. Okay, so it becomes very unstable. Why? Because you're not saying that the target is dependent upon 10 variables, but rather it is probably sensitive to 200 variables. You're saying that the model is very unstable. It is dependent upon 200 variables. It's sensitive to every variable that you see here. Or probably you need too much of computing power to crunch a big data set like this. This is what is called as curse of dimensionality. So the number of columns is not 10 columns, you're being shared with 200 columns or 200 variables. Using 200 variables in a predictive model is what we call as curse of dimensionality. Why? Because there are too many coefficients to estimate, which means you need a very good computing power. Or since there are too many coefficients, your model is going to be very sensitive or kind of unstable. Hence, what we do is, guys, we follow two popular procedures. One is not dimensionality, I'll call it as variable. Okay. One is something called variable selection procedure. Number 2 is variable reduction procedure. So what do we have? We have number 1, which is basically variable selection procedure, and number 2 is basically variable reduction procedure. What is the difference between variable selection and variable reduction? Now suppose in case you have a target variable y and you're given predictor variables, let's say like 200 predictor variables. If I go back and check what is the direct effect of a predictor on a target, what are we doing? We are asking the question, what is the effect of a predictor on a target? Individually, we are going and evaluating. And post evaluating, if you get to find that that predictor is having a direct effect on the target, you retain those predictors. The other predictors you may probably drop it. That is what is called as variable selection. So you guys might have come across something called correlation, isn't it? What is correlation? You're trying to understand the linear relationship between a predictor and a target, isn't it? So between x1 and y, we are trying to understand the linear relationship using correlation. If they are kind of related to each other, you say, yes, it's a good predictor. I can probably use it for my predictive model. You'll retain it. But some other predictor, since it's not correlated with y, we will basically filter it out. We will remove it. So keeping only the variables which has direct effect on the target is called variable selection, right? Removing it or keeping it is exactly what is called as variable selection. Whereas on the other hand, variable reduction is basically a mathematical transformation that you will do on the data set. So what is a variable reduction procedure? It's more like a mathematical transformation that you're doing. So you're given a capital X number of predictors or a data set like this. You do a transformation and you come up with a new set of data, which is X prime. So it's a mathematical transformation that you're doing. X will basically become X prime here. This mathematical transformation is called as variable reduction procedure here. Example is something like PCA. It doesn't depend on the target, guys. Variable reduction doesn't depend on the target, but variable selection depends on the target, because you're doing statistical analysis and you're kind of comparing a predictor and a target at a single time. How are they related? So you need the target all the time. That is variable selection. When you don't need it, it's called variable reduction. You're basically taking your capital X, you will apply some transformation to come up with X prime. Example, PCA is a mathematical transformation. We call it as an orthogonal transformation, something we'll discuss probably in the next week or something. So it's an orthogonal transformation. So you're basically doing a linear orthogonal transformation. It's a mathematical transformation you will do, and you'll convert a data set which is capital X into X prime here. So what we are seeing right now, the multilayer perceptron is actually speaking doing dimensionality reduction. Can you see? So example, if I had 150 rows and 50 columns, that input would right now would have got reduced to 150 rows and 6 columns only. Why 6? Because we have only 6 perceptrons right now. Similarly, later on, what is he doing? This 150 cross 6 will basically become 150 cross 4 right now, right? So we had 50 columns originally. Those 50 columns, whatever is the pattern that they are having, has got transformed and it has got combined in 6 columns. The predictive capability available in these 6 columns have right now got combined or transformed into 4 columns right now. These 4 columns might later on become 2 columns. Then the 2 columns later on might become one single column, which is nothing but the output that you wanted. So you can see, right, how it is actually doing dimensionality reduction. It's saying, hey, you give me a bigger image. Using neural network, I'll make it as a smaller image. So all of us are looking at YouTube, right? So today we have what? 4080 pixel videos and all. Then what happens? You get 2000 pixel videos. Then you're probably getting 1080 pixel videos. You're getting 512 pixel videos. You get 256. You get 128 pixel videos. Whatever it is, The music video that you're watching is still of the same quality, right? I can still see the same artist singing in all the same area. The information is kept as it is. Probably the quality would have come down, right? A little bit of quality loss will be there, right? Quality loss will still be there. So what you're saying is the information available in a pretty high definition video is still kind of retained in a small lesser definition video. The information is still there. I can still perceive it. Probably here it was 100% of the data, but here I'm retaining only 60% of it. This is an example of dimensionality reduction all of us see on a day-to-day basis. PCA is one common algorithm that everybody was using all these days to convert videos to a lesser density video here. PCA. It's a mathematical transformation. Today it's all neural networks. Neural network is saying, hey, a bigger video, something like this, I can reduce the resolution for you with the same information. I can reduce it further using some other layer and same information. I'll reduce it further, I'll reduce it further, I'll keep reducing it. Whatever the PCA was doing, now a neural network is actually doing, or whatever today YouTube is using is basically the neural network models that we see today, right? It's basically doing something called as dimensionality reduction here, guys. It's taking up our data sets and it is reducing the data set size. So instead of having 50 columns, I'll keep the same information in 6 columns. I'll have the same information 4 columns, which will become 2 columns. And finally, it will become 1 column. Why? Because I've kept only one single perceptron. So if I keep 1 perceptron, I'll get 1 output. 2 perceptrons, I'll get 2 outputs. 3 perceptrons, I'll get 3 outputs. So the number of perceptrons in the last layer will decide how many ever outputs we want. That is why going back here, I said we will get 2 outputs. Why? Because there are 2 perceptrons here. That's why you will get 2 outputs here. If I kept another layer with a single perceptron, I'll get only one single output. It will basically merge the 2 outputs together, right? So this is exactly how a multi-layer perceptrons max at the back end will basically work, guys. It's all matrix multiplication. We're going to quickly see an example, okay? But before I jump into it, this is exactly how you need to basically understand how a feed-forward propagate algorithm will work. So what is the feed-forward propagate? I'm passing on my inputs. It passes through the random weight and biases he has assumed for now. Then he will just push it on the inside. He'll multiply, he'll compute everything, and he'll come up with an output here. That is called as feed-forward propagate. The next stage is backward propagate, which is basically passing on the errors in the reverse fashion and asking all the neurons to basically get kind of trained. That is something that we'll discuss in a minute. But before that, this is exactly how a feed-forward propagate is typically going to work. And these are the dimension calculations that we've just seen. And what is he actually doing? He's trying to do something called as dimensionality reduction. This is a property that has been exploited by a pretty popular model in multilayer perceptrons, something called as autoencoders. We're going to be discussing this one. So autoencoders is a classical usage of this dimensionality reduction property in a multilayer perceptron. So autoencoders is something that you guys might have come across, right? You would have heard it pretty often. It's a popular practical usage of the dimensionality reduction procedure that is available inside a multilayer perceptron. So we are going to design an autoencoder, in fact, later in the day. Okay, so this is exactly how a feed-forward propagate model is basically going to work, guys. Or sorry, a multilayer perceptron model is going to work in the feed-forward stage. Tell me, guys, any questions till here? Are you all able to follow what exactly is happening? The math at the back end, how the matrix multiplication is happening? Why are we getting these outputs? Why do I call it as dimensionality reduction? Does everybody agree? Yeah. Okay. Okay. So now let me ask you all a quick question. So I'm actually designing a network like this, okay? I have input. Let us probably assume there are 150 rows and 15 columns with me, okay? I add my first layer with 4 perceptrons. I add my second layer with 10 perceptrons, the third layer with 15 perceptrons, and the last layer with 2 perceptrons, okay? And the same input, 150 cross 15. The first guy is 10, the second guy is 8, the third guy is 4, and the last guy is 2, okay? So my first question is, how many outputs can we expect here, or what is going to be the dimensions of your final output? Can you all tell me the dimension of my final output in both the layers? Okay, a small request, guys, please give me your answers as a private message so that I get to evaluate how others have understood also. Okay. So what is going to be the output? So it's going to be 150 cross 2, correct? Why is it 150 cross 2? Because there are 2 perceptrons at the last layer. So for every data point you have, for every row, there is going to be 2 outputs. That's why it is 150 cross 2 in both the cases, correct? So I have 150 rows. Every row will give me 2 outputs right now. So one could be how much of brake I need to apply for a car and how much of acceleration I need to apply, right? So these are the 2 outputs he's going to tell us. Good. Now let me ask you all a quick question. Do you think architecture number 1 is correct or architecture number 2 is correct? Or do you think both is okay? And what is your reason behind it? Do you think 1 is good or 2 is good? Or do you think is both okay? And what is the reason behind it? So is the architecture 1 okay or architecture 2 okay? What is the reason behind it? Okay, perfect. So I think everybody has given me an answer saying it is the second guy. Why? Because you can see that, from 10, 8, 4, 2, I can see that, the dimensions are getting reduced in a gradual fashion, right? 10 becomes 8, 8 becomes 4, 4 becomes 2. Perfect, good. Now let me ask you all a question. I'm making it as 16, 8, 4, and 2. Is 2 better or 3 better? Tell me. Okay, so Anu, I get your answer. The second one, you told me that, I mean, for the previous question, so you told me that reducing the dimensionality of the perceptrons. Agree. Now, for this question, what do you say? Is it the second one or the third one? And why do you say so? Which one is good? I want a reason. Why are you saying 3 is better? Okay. Okay. So Sanjay, you're saying that we're going to have a standard reduction in stages, hence there might be some computation benefits. Okay. Okay, so I think Yatinder has a point. Good. I agree with everybody's answer saying that it is a third one. Perfectly right. But why do you say so is something that was not very convincing. The most of the answers that you gave me. So I think the answer is simple. One is because I had 15 features, correct? The 15 features was basically probably blown to 16, or even let me assume 14, So the maximum amount of information available in 15 can be captured better by 14 people versus the 10 people that you might have kept in the previous case, right? So the amount of information available in 15 variables will be captured better by 14 people compared to 10 people at the first layer. So what I would tell is, compared to the second architecture, the third architecture first layer is capable of capturing more amount of information. So the second layer may not have that much of information to probably capture or capability to capture that much of information, but the third layer is, so third architecture is sure shot going to capture a lot of information because 14 perceptrons compared to 10, 14 is going to work better. Then the 8 people are going to enhance the output coming from 14. The 4 guys will enhance the output coming from 8. The 2 guys will enhance the output coming from 4. So the point is that, guys, the number of perceptrons should always keep reducing as you go further. I think now everybody has the reason why. I'm pretty sure everybody understood by the answer you gave me for the first and seconds comparison. So number of perceptrons should basically keep coming down. Why? Because the information should get condensed as it goes over the next layers. Bigger information should get condensed, get condensed, and keep going on. So the information should get condensed. You can't have the information to get bigger and bigger. It becomes more noisy. So you're saying, hey, I have a 4080 pixel video. I'm condensing it to a 128 pixel video. Versus initially itself, when you capture it as 128, and when you try to blow it up by 4080 pixel, the quality is surely going to be bad, right? So, Abhishek Bachchan is going to look like Amitabh Bachchan. I'm just saying. So whatever is the information that is available here, you won't have it in a proper fashion, or opposite. I'll say Amitabh Bachchan is going to become like Abhishek Bachchan. Okay. So the information at the very first layer, right, will not be kind of passed on or will not kind of become better going further and further. It's going to become more noisy is what I would say. While here itself, if you capture the higher amount of information, you can keep reducing it. So this architecture is something that we don't want. We want the first case where the bigger information is getting condensed as it goes further. So the next point is keep maximum number of perceptrons in the first layer. I think it's the same reason why. From the image, try to capture maximum amount of information possible, right? So you can't have lesser amount of information captured in the first layer, which you're trying to enhance it further. That's completely bad. Maximum information capture should happen at the first layer, which is possible only when you have many number of perceptrons. So make sure that initial layers are having many perceptrons. They should have many perceptrons as much as possible because they capture the maximum information. So you can't have like 10. Rather, a 20 is better over 10 or a 30 is better over 20. So have maximum number of perceptrons at the initial layers because they tend to capture the most amount of information, which is getting enhanced or kind of getting better and better as it goes further in the network here. So keep decaying the number of perceptrons as you go further, and keep the number of perceptrons always high at the first layer. The last question we need to understand is, how many layers should I probably keep? That is an answer we will see practically. So typically how it works is, basically it's a black box, okay? You can't really decide an architecture so easily, and you don't know the reason why it works like this. Why does 8-layer work better than a 6-layer or a 5-layer? You can't really answer. So to basically decide how many layers, right, there is a usual procedure people follow practically. First time you create a very complex model. You create a complex model. It's the same thing like what we did in decision tree, guys. Decision tree pruning mechanism. Do you all remember? What will happen? He'll create the maximum level of decision tree possible. Then he will start deleting from the bottom. Same case. Create the most complex model that is possible. That is the most complex neural network possible. Then start deleting the layers from the back. So you create the most complex model. The error could have been, let's say, 1,000 units. Now you delete the last guy. It might have improved to 900. You delete the last guy. It might have improved to 800. You delete one more guy. It would have improved to 700. You delete this guy. It'll go to 1,000. Then you know, okay, till here is what I should keep. The rest of the people alone, I can delete it. So this is how we practically do it. So there is a two-way approach, okay, where you add one layer at a time and you see the improvement in the result, or you delete one layer at a time and you monitor such a fashion that the result doesn't go bad. So here you might have got 10% accuracy. It might become 20, it might become 30, it will become 40, or let's say I'll assume 80. Further on, it doesn't improve at all. Then you decide, okay, these layers are not required. Or here it was 80, here it was 80, it was 80. If it comes down, then you say, okay, I think I need to stop it here, which means I can delete these two people till that my accuracy was okay, it was stagnant as it is, but later on it started going down. So which means these two people are redundant, I need to keep it till here. So it's more like an addition or a subtraction method. You can use anything. So the number of layers is something that we just solve it practically. We don't have a theoretical reason on how to tune it or how to keep it. We just have to do it practically. So keep adding one layer and see the improvement, or keep deleting one layer and see through that it doesn't degrade. So these are the two methodologies by which you can tune the layers available in your multi-layer perceptron model. Okay. So now let's go back, guys. Multi-layer perceptron, 3 properties to be worried about. What are the 3 properties? Architecture, activation function, training algorithm. Now tell me, in architecture, how many layers to keep, or at each of the layer, how to keep the perceptrons, how many perceptrons to keep? Do you think you have an answer for this question? So how to design the architecture for a multi-layer perceptron? If this is a question that is asked, do you think you guys have an answer right now? Do you think you can answer this question? How to design the architecture of a multi-layer perceptron? How many layers can I keep? How to design the layers? Do you think you'll be able to do it now? Yes or no, guys? Right? Okay, perfect. How about others? I didn't see an answer from Avi or Manjeet. Manjeet, I didn't get an answer from you. Jinisha, if I'm not wrong. Yep. Okay. Guys, feel free to say no. If you have not followed, it's completely okay to go back and repeat. As I keep saying, right, I'm pretty sure everybody would appreciate it, in fact. Okay. Okay. So I think the first point of how to decide on the architecture of a multi-layer perceptron is something that we just discussed, right? We are done with it. So the next thing that we're going to do is discuss about activation functions. By the way, there is a small piece to it. I would say there's another 5% of things that we need to discuss about architecture. I've subtly given you the idea, but still we need to revisit back on this architecture piece. So the next point that we're going to discuss is basically activation functions. Okay. What do you mean by activation functions? So at every perceptron, after he is doing input into weights plus bias, right, I can apply a function on top of them. So if this is an output, the output can be pushed into a function. It's an activation function that I can apply. I can apply exponential, I can apply log, I can apply sigmoid, I can apply softmax, ReLU. There are a lot of functions available. Now the next point is basically discussing about those functions here and what is the role of these functions. So there are a list of activation functions that typically people use in deep learning, guys, and probably even available here in Keras. So these are the list of functions you're going to discuss: sigmoid, step, tanh, arctan, rectified linear units, leaky ReLU, soft plus. So these are the 7 different functions we're going to discuss right now. 8th function is softmax, which I'll come back after this one. So in fact, one of the first function is identity or linear. That is, if you don't specify any activation function, right, by default it is linear, or also called as identity, which means he is just doing an input into weights plus bias. That's all. It is not applying anything on top of it. It'll leave it as it is. It's an identity function. So the linear function or an identity function is something that might happen by default. But apart from that, there are a lot of other activation functions available. Let me ask you all a question. What do you guys think is the role of an activation function in a neural network? What do you think is probably the role of an activation function? Yes, guys? What do you all think is probably the role of an activation function? Good. That's a good answer, Yatinder. So Yatinder is saying, probably when you want to make your model nonlinear, you can use it. Good. Yes, any other reasons? Okay. So I think I'm agreeing with the first answer, where probably when you want to make your model non-linear, you can start using activation functions. That's good. I think I have another answer here. So to suit the required output or distribution style, that's a perfect answer. That's exactly the answer I was expecting. And there's another answer: to deal with classification regression problems. Once again, a beautiful answer. Goes pretty much, same with the previous point that we just told. So the point is that, guys, activation functions are not just useful for making the output, nonlinear, or making the model nonlinear. It is also desired, when you probably want to, bring your output in a particular fashion or in a particular style. So say for an example, we wanted our output to be what? A classification output, which can probably be probabilities, which was a logistic regression model. What did you do? You kept a sigmoid function at the last. But rather you wanted the output as it is, which was a linear regression model, you kept it as linear here, right? So I'm totally agreeing with the answer, which is the kind of output that you want, right? That is typically decided by the activation function that we see here. So do you want an output only between 0 and 1? Use an activation function which will give you so. Or do you want an output coming from -1 to +1? Use an activation function which will give you like that. Or do you want it completely linear, which is -infinity to +infinity? Do not use any activation function, right? Another point is whenever you want to make your model to work non-linearly, you start using activation functions. So these are the two reasons on why we use activation functions within our multi-layer perceptron models here. What are the list of activation functions available? You can see here. Okay, so I think Sanjay has a question. Do we mostly use the activation function at the output stage? No, not at all. Not at all. So let's say you're creating a multi-layer perceptron. The output you want is probability 0 to 1. Instead of compressing it at the last layer, you could have compressed it even at the previous layers itself, right? So it's like, I'll give you a common logical answer telling why it shouldn't be kept only at the last layer. So here you're saying, hey, input is passed to 2 people, which is 3 people or 4, which is passed to 2 people, which becomes a single. So here also you can keep sigmoid. I can keep sigmoid even here because they will also give me probabilities, right? Here also I can keep a sigmoid. They will also give me probabilities, which will finally become once again a probability. It's equivalent to saying 4 models are predicting probabilities, which is chosen by 2 models, which is finally chosen by one single model. So 4 models are predicting probabilities, where 2 models are telling how much weightage to give for each of these 4 models, or they are choosing the right models. And then the last guy is once again choosing the right one from these 2 people. So you need not have linear outputs here and only convert it as a sigmoid here. Need not be. You can convert them as probabilities starting from here itself. It's completely okay. So you can have activation function at every layer. That's completely okay. And in Keras, once again, just like bias, right? Activation function is for the entire layer. You can't keep it at a perceptron level. Entire layer will take one activation function type. You can't change it for every perceptron, unfortunately. If you want to do it, go back to TensorFlow. Okay. That's a good question. Thanks for asking. So let's go back. I think our point of discussion was about what are the different activation functions we have. Okay. So let's jump into sigmoid. I'm pretty sure everybody knows what is sigmoid, right? E to the power of x divided by 1 plus e to the power of minus x, right? So you can see here. The reduced form of this guy is 1 by 1 plus e to the power of minus x. So this is a sigmoid function. I am generating certain inputs starting from -4 to +4. I will just plot that input on the x-axis and the sigmoid of the input on the y-axis. This is how the curve is going to look like. Okay, so this is how the curve is going to look like. So sigmoid will basically help us find probabilities running between 0 to 1. Example, logistic regression model. So whenever you want to create a classification model which will give you a binary outcome like 0 and 1 or any probabilities between 0 and 1, please start using sigmoid. Next popular function is step function. What happens in a step function is if it is greater than 0, it is kept as 1, else it is kept as 0. So now you can see for the output value, if it is greater than 0, it is kept as 1, else it is kept as 0. So you can see that it will be perfectly like a binary outcome, 0 or 1. Now say for an example, you want a classification model which will predict probability. I'll use sigmoid. But if you wanted a classification model which will directly give you only 0 and 1, I would use a step function. Getting it, guys? So I would use a sigmoid if I want probability. But if I say, no, I'm not interested with probability, I just need the direct outcomes, what is 0 and what is 1, I would prefer a step function. Similarly, if somebody is interested with a -1 to +1 answer, you need to make use of something called tan h. Okay, so tan h formula, if I'm not wrong, mostly I'm wrong. Tan h is something that I always get confused. It should be, it's better I Google. Okay, it is e to the power of x plus e to the power of -6 divided by the same thing in a minus fashion, I think. He's giving it to the whole series. Okay. There should be that e to the power of x plus, what is that formula? Tan h is here, this guy. Okay, e to the power of x minus of e to the power of -6 divided by the version of it positive. So I was wrong. I told positive first and then negative. So you have it here. So tan h formula goes like this. So e to the power of x minus e to the power of -6 divided by the same version in a positive fashion. That's all. Okay, I actually interchanged it. I knew it. I always do. So this is basically the tan h formula. So this guy will basically be the hyperbolic tangent, which is otherwise, the same kind of a S-shaped curve. But the difference is he's going to run between -1 to +1. Can you see here? So tan h goes something like this: e to the power of x minus of e to the power of -x divided by the same version, but between that you need to add it, not subtract. It becomes tan h. So tan h is going to run from -1 to +1, something like this. Whereas the sigmoid is going to be between 0 to 1. They're both S-shaped curves, but tan h can be used when you want outputs between -1 to +1. Example, support vector machine. There is a classification model called SVM, support vector machine. Support vector machine is a model that will predict -1 and +1. Okay, so support vector machines typically needs outputs as -1s and +1s. So he is somebody who can probably be replicated by using a tan h function here. But if it's probably 0 to 1, you'll have to use sigmoid. Then arctan, which is nothing but tan inverse of theta. Okay, that is called as arctan. He is also going to be something like this, but he runs between -1 to +1, almost like the same version of it. Okay. So now let's come to this one. This is a very important function, guys. It's called rectified linear units. Okay. So this is a very latest addition to the deep learning models, rectified linear units. It's actually a linear unit, but it's rectified, which means to a certain area, it is actually speaking kind of non-linear. So what is a rectified linear unit? It's very simple. If your x value is above 0, it is kept as x, which is it is kept as it is, else it is made as 0. Okay, if x value is above 0, it is kept as it is, else it is kept as 0, which means if your x values are anywhere below 0, they will all be made as 0, but the moment it is above 0, it will be kept as a straight line like this, a linear line, something like this. This is what is called as a rectified linear unit. See here, guys, we are saying x into x greater than 0. X greater than 0 will do what? It will give you true and false. If it is true, the x will be kept as it is. If it is false, it will be made as 0. Let's hit control enter. This is basically our ReLU function. Let's hit control enter. Here you can see this is how the rectified linear unit is going to work. So what is actually happening is, guys, if the values are on a negative scale, right, this negative portion will be made positive. That's all. The positive portion will be kept as it is. This is what is called as ReLU, or rectified linear units. So this is a very popular activation function that was very recently added to the deep learning frameworks. It's very popular because it will enhance the performance of your predictive models. I'll tell you why. Okay, probably in the second half of our session, you'll understand why it is so. It solves a problem, something called vanishing gradient problem. Okay, so there's something called as vanishing gradient. That is a problem that this rectified linear unit can solve for us. So we're going to discuss about this guy. Okay, rectified linear units in pretty much in detail in coming second half of the session. Similarly, there's something called leaky ReLU. In leaky ReLU, what you say is, you're saying, hey, let it not be made as perfectly zero, okay? Probably we can make it as 0.1 times of x or 0.01 times of x. That is what is called as leaky ReLU. So it's not perfectly made as zero, but it'll be made like 10% of the original value. So it'll still be what? Something like this. It'll not be flat like this, but it'll be something like this. That is called as a leaky ReLU. Once again, a latest addition to the deep learning frameworks, and it's been pretty, popular. So you can see, if it is above zero, keep it as it is. But if it is below that, multiply it with the alpha. Okay. So you can decide what is the alpha. But if you're keeping an alpha of 0.01, it's called a parametric ReLU. So I'm not very sure why there is a special case for this one, but I've heard that from one author that it's practically very good in performance when you keep like 0.01. That's why they've given a special case called parametric ReLU itself. So now let's go back and check it. You can see we are keeping 0.2, which means 20% of the x is what you should be showing. So this is exactly how the leaky ReLU will look like. If you're keeping 0.01, it will basically be your parametric ReLU. Okay. So this is leaky ReLU. When you keep 0.01, it becomes parametric ReLU. And last, over to something called soft plus. Soft plus formula goes like this: log of, within the bracket, 1 plus exponential of x, which is actually pretty much close to the ReLU that we have seen, but the transition will be much more smoother. That's all. Just give me a second. Sorry. So soft plus is basically another function. It's written as log of 1 plus exponential of x. The only difference is that compared to the ReLU, it's going to be much more smoother while it is transitioning, through that zero, I would say. It's not like perfectly cutting from zero and becomes a linear. It's actually much more smoother. So the blue color line that you guys see is the smoother version, the soft plus that we are talking about, while the orange one is basically the original ReLU that we've already spoken about. So these are the list of activation functions available, guys. But there are several other activation functions there. You can just go back and Google activation functions. In Wikipedia, there's like, there is a beautiful article. So you can read about this guy. There's a list of functions here. Identity, binary step, we have spoken about. Logistic or sigmoid, we do know it. Tan H, we have spoken about it. Arctan, we know it. Tan inverse of X. Arc sin H and all. Right, inverse square root unit, there's a lot. ReLU, we just spoke about it. Then we have leaky ReLUs, right? And it becomes parametric when the alpha is 0.01, right? Or was it the opposite? Parametric is alpha. For leaky, it is 0.01, is it? Okay, so I think there's a small change. Okay, even I've done it like this. Sorry, guys. So even here it's like this, but unfortunately, while I was just reading it loud, I made it wrong. So leaky ReLUs are when alpha is 0.01. Okay, otherwise it's called parametric ReLU. So the parameter is the alpha that we're talking about. I'm sorry, guys. So if it is 0.01, it is leaky. Else it's called parametric. Okay, I'm sorry, I'll just take it back. So generally it's called parametric ReLU, but only when alpha is 0.01, it's called a leaky ReLU. Okay. So just go back and see, randomized leaky, exponential linear, many other functions, soft plus that we just spoke about, right? Sinusoid, sine, Gaussian. And many of these are not supported in your Keras and all. Some of these are. Even here, not everything is supported. Some of these are supported. Okay. So these are the different activation functions available, guys. There's a reason why everything is available. So you can see the range. Minus infinity to plus infinity, it should have been identity. Perfect 0 or 1, it is binary. Or anything between 0 and 1, you can see the bracket change. Curly brackets versus plain parenthesis. It's called logistic. Between -1 to +1. Arctan is -π/2 to +π/2. Right? So you can see there is always a range attached for every function. So depending upon the range and the way they're working, you might choose different activation functions from this list here. Okay. So this is the second point that we need to discuss. What is activation function? What is its role? The role of an activation function is probably to make a model nonlinear, or to probably, make your model to give you an output which is, on par of what we want. Okay, it's going to give you an output which is something that we want. So those are basically decided by the activation functions that we're using. Okay. First point, architecture. Second point, activation function. So now tell me, guys, are you all convinced with this one? Architecture and activation function. Yes or no? Both the points. How to decide architecture? How to decide activation function? What are the activation functions available? Yes or no? And as I told you all, connecting both these points, there is one small thing that we need to discuss. We'll come back in a use case. But before that, till here, are you guys okay? Architecture and activation function. Any questions? Looks good. Okay. Okay. So let's go for another 15 minutes and probably post that. Let's take a break. Okay. Let's have a quick use case discussion. Okay, small case. So I think it's going to take 15-20 minutes, and probably after that we can jump into a small break, and then let's be back. Okay. Let's have a next round of discussion again. Okay, so before that, Yatinder had a question. So would I be sending the instructions on how to install Keras? Absolutely yes. Expected by tomorrow afternoon or something, the PPT, everything, recording, everything should be available. Okay, or I'll try to make it by today evening itself, but worst case, by tomorrow afternoon, it should be there. Okay. Great. Okay. So let's just discuss one more thing, guys, to not leave the continuity. The small portion that I wanted to kind of discuss, something that's common for the 2 points that we're discussing here. So let's jump into a small example, a small case, shall we? Okay, thanks, Anu. Let's jump here. Cool. Okay. So what we're going to do right now is, guys, we're going to solve a classification problem, okay? So why am I interested in a classification problem and not in a regression problem is because there's one small point all of us should understand, okay? Basically, the architecture in the last layer is something that you need to watch over, okay? The last layer architecture is something that we need to basically understand. One is architecture. We have followed that, the number of layers should keep increasing. The number of perceptrons should keep decreasing at every layer. First layer should have maximum number of perceptrons. But we didn't talk about the last layer, correct? Now, say for an example, guys, let me give you all a small problem, okay? I want to create a self-driving car. I'm assuming that the model is supposed to predict 3 things. One is he has to tell me how much of steer I should be doing, okay? Clockwise, anti-clockwise, tell me, give a 30-degree steer or a minus 30-degree or a plus 60-degree or a minus 90-degree. He has to tell us how much of steer that we have to give, and also tell us how much of acceleration and how much of braking. Let's assume it's a stickless car. So we are saying steer is one output that you need to predict. Another is how much of acceleration. Another is how much of brake. Now the point is simple. It's going to be a regression model, right? So tell me guys, how do you think I can solve this particular use case where I want you all to create a predictive model? One, or I don't know, I just say create artificial intelligence which will predict three outcomes. One is how much of steer, how much of acceleration, and how much of braking. How do you guys think you can solve this particular problem? Any thoughts? So basically, I want you all to create some intelligence which will help me create a self-driving car. And the intelligence is supposed to predict three things: how much of steer, how much of acceleration, how much of braking. If I were to give you this objective, what would you guys do? Yes? Is there no answers, or are you guys typing something pretty big? If you're typing, I'm ready to wait. Or let me ask you a question like this. Let me wait for a minute if anybody is typing for this question. Okay. Okay. Good. Good one, Yatinder. Good. That's the question I'm going to ask you. So tell me, guys, do you think this has to be solved with three predictive models, where one model will predict how much of steer, another guy will predict how much acceleration, and the third one will predict how much brake? Do you think we need to come up with three models? So how many of you agree? Yes or no? So I'm saying I need to come up with three predictive models here. Each of these models will predict one outcome. What do you guys think? Is it a yes or a no? Okay. Yes, Anu, what's your answer? Manohar, Divya, Nizam, Sauvik, Sanjay, Ravi, Rakesh. Okay. So I'm saying that you need not create three predictive models. Okay. Okay, Divya. Okay. So what I'm saying is that, guys, you need not create three predictive models here. I'll give you a reason why. You can't create three predictive models because all the three models, may not work in sync, actually speaking. Or all the three models might have probably had different kinds of parameters is what I would say. At one situation, one guy will say, hey, accelerated, while another guy might say probably brake it. or in a situation where there is probably some people crossing or there's a red light, one guy would say, accelerated, another guy might say, hey, brake after some time, right? So you can't create three predictive models. All the three people may not work in a synced fashion. That's going to be a problem. So what I would say is you need to go back and create only one single predictive model. We need to create one model, but that one model should predict three outputs for us: output 1, output 2, and output 3. Tell me guys, how do you think we can make a predictive model predict three outputs? Where do you think we need to play in the architecture piece to get three outputs? If I want to create a predictive model which is going to predict three outputs, the steer, acceleration, and braking, where do you guys think we should probably middle with in the predictive model? What do you think we should probably do? Look at this, Max. This will give you your answer. So what are we supposed to do, guys? We want three outputs, right? So we are saying, okay, let me pass the inputs, whatever you need. You can keep as many layers as you want, but the last layer is going to be the output, correct? So what will happen? Input is going to be number of data points times number of features. The output is going to be what? Number of data points times number of perceptrons in the output layer, correct? Now tell me guys, how do you think I can get three outputs? What should I probably do? Give you the answer. Exactly. So we should have basically kept three perceptrons in the last layer, isn't it? So what should we do? We should basically keep a last layer which is having three perceptrons. So you're saying, hey, I might have had for every data point, even 150 features is okay, but I want what? An output which is having the same number of data points, but for all the people, I need three predictions. One prediction of steer, another prediction of acceleration, and the third prediction, which is brake. So I need three columns. The three columns are nothing but the number of perceptrons in the last layer. So the number of perceptrons in the last layer should ideally be equal to 3. So the last layer architecture is something that you need to be really, careful about. The number of perceptrons in the last layer is equal to the number of outputs that you are expecting. Let's please keep that in our mind. What are we supposed to do? We are supposed to keep the number of perceptrons in the last layer, which is equal to the number of outputs. Because you know the max. Input is number of data points into number of features. It became number of data points into number of perceptrons in hidden layer 1. It becomes number of data points into perceptrons in hidden layer 2. It became hidden layer 3. Then it becomes output layer. In output layer, we should have 3 perceptrons. Only then I'll get 3 columns of output. So the number of perceptrons in the last layer is always equal to the number of outputs, guys. Let's please keep that particular point in our mind. The second thing that you need to be worried about in the last layer is what? Basically your activation function. What activation function should I keep? If it is a regression problem, what activation function would you guys keep? Can you all give me an answer? If it were a regression problem, what is the activation function we should have kept? Good, exactly. So it should be linear, or also called as identity, because it will give us answers coming from minus infinity to plus infinity. Regression problems are continuous outputs, which will be anywhere between minus infinity till plus infinity. So it should be a linear function, or also called as identity. Perfectly said. If it is classification, what is the activation function you guys will keep? Very good. Very good answers. Yes, I'm just getting 4 or 5 answers. How about others? If it were classification, what is the function you would have kept? Good, good. So even though your answers are correct, yes, what most of you told me was sigmoid as an answer, but it is conditions applied. It can also be something called as softmax. You can either have a sigmoid or you can have a modified version of sigmoid, somebody called as softmax. So in regression, yes, number of outputs I'm expecting should be basically equal to the number of perceptrons I'm keeping. Even for a classification, if I'm going to predict, let's say whether a particular photograph is a car or a bike or a truck, there are 3 possible outcomes. So I should predict, hey, there is 80% probability it's a car, 10% probability it's a bike, 10% probability it's a truck. So there are 3 outputs he's predicting. Even for a classification, yes, number of levels in the target variable will be equal to the number of perceptrons. Second point, as you all told me, activation function, if it is regression, I would keep linear identity. I completely agree. But for classification, conditions apply. It's only for a classification, guys, that we need to understand that there are 2 kinds of classifications that we can do. Okay, classification problems are typically divided into 2 classification types. The first case is called as a mutually exclusive case, and the second case is called as mutually non-exclusive case. So first one is mutually exclusive, second is non-exclusive. What is a mutually exclusive? As the name says, if I give you one photograph, you give me one exclusive outcome. You tell me whether it was a car or whether it was a bike or it was a truck. It can be only a car or a bike or a truck. It cannot be all the 3 or any 2, anything like that. It cannot be like that. It can be any one. It can be a car or a bike or a truck. It's called as an exclusive outcome. What is a non-exclusive outcome? A non-exclusive outcome is a case where you say, in this photograph, I can see a car or even a bike or even a truck or even all the 3 together. So the photograph might have a car or even a bike together, or a bike and a truck together, or car or truck, or even all the 3 people together. There's chances of more than a single prediction. You're saying it's not exclusive, boss. It can be more than one. Once again, look at this particular diagram. It's an architecture that we have designed where we are predicting the iris data set. You have a single target, but what are the different classes we have? Setosa, versicolor, and virginica. So I need to come up with what is the probability it is Setosa, what is the probability it is versicolor, what is the probability it is virginica. So there are 3 probabilities we need to estimate. Since there are 3 outputs, we are keeping 3 neurons here at the last layer. Now everybody should agree with the rule number 1. What is the classification you're going to do is the next question. Do you want to tell that this particular flower that we are having is only Setosa or versicolor or virginica, which becomes a mutually exclusive case? Or do you think you can have more than that? Do you have both flowers or 3 flowers in a single photograph? It becomes a non-exclusive case. In a non-exclusive case, guys, you should be using a sigmoid function at the last. What should you be doing? You should be using a sigmoid function at the last. I'll tell you why. You should use a sigmoid function because it is almost creating 3 logistic regression models. It's almost creating 3 binary logistic regression model. where the first perceptron will tell you what is the probability it is setosa. Second perceptron will tell you what is the probability it is versicolor. Third perceptron will tell you what is the probability it is virginica. So what is going to happen? Each of these perceptrons will tell us what is the probability that this particular class will occur. So first guy is telling, hey, I am the probability for setosa. Second guy tells you, hey, I'll give you the output for the probability of versicolor. The third perceptron tells you, hey, I'll give you the probability that it is virginica. So it is like three logistic regression model. He will basically do probability of S versus not of S. He will say probability of versicolor versus not of versicolor. Probability of virginica versus not of virginica. So he's almost like creating three logistic regression model. So first guy will tell, hey, 80% chance it's setosa, 60% chance it's versicolor, 75% chance it's virginica. What do you want? You want non-exclusive case. So you will keep a benchmark. Okay. So any classes which is above 70, right? Go back and fetch it is what you will keep. Some threshold you'll keep. So who's above 70? Setosa is here. Virginica is here. So you'll say, hey, this photograph is having setosa as well as virginica. That's it. So it's like three individual logistic regression models, guys. So it's the same input, same photograph. All the three people will try to tell. The first guy is saying, hey, I have a car at this rate. Yeah, I think there is a bike at this rate. The third guy is saying there is a truck at this rate. So there might be an image, okay? Here it could have been a car, here it could have been a truck. So first guy is saying car at 80%. Second guy says bike at 0. Third guy says truck is here at the rate of 70%. Since both of the models are saying that there is a above 50 possibility that this class is happening, you will say, okay, there is a car, there is a truck. This is a non-exclusive case. What is an exclusive case? You are basically saying only one outcome is possible. Out of the image, just tell me if car is there, or bike is there, or truck is there. In that case, guys, what we will do is, we'll still have a sigmoid only, obviously. He will give us three probabilities, okay? First guy is telling us, hey, there is a 80% probability of having a car, 60% probability of having a bike, 75% probability of having a truck. Now I'm posing a question to you all. If I want an output which is exclusive, which is completely exclusive, only one outcome I want for a given image, what would you guys predict out of all the three cases? Do you think it's a car or a bike or a truck? Exactly. Everybody is going to agree on a car. Why? Because everybody will think, hey, he has the maximum probability, right? So you will say, hey, it's a car because he has the highest chance. So you're saying 80, correct? So you're saying, hey, this particular image is having a car. So now somebody is asking you, what is the probability that it is a car? What would you guys say as an answer? So you told me it's a car. If I ask you, okay, what is the probability that the model is predicting? What is the answer you will tell me? Exactly. So you will tell me 80% probability, correct? I hope everybody agrees with this 80. Now suppose in case the guy is asking you, okay, what was the chance it could have been a bike? What is the chance it could have been a truck? What is the answers that you guys will give? So all these days we were creating logistic regression model, right? So when somebody asked us, hey, what is the chance that the customer will respond? We said 70%. What is the chance he will not respond? It was 1 minus 70, which was 30%, correct? Similarly, I'm saying for car, you told me 80. Not of car is what? Bike and truck. What are the probabilities you guys will give me for, both the cases here? Okay, 0.2 for bike, truck together. Okay, what happens to bike separately, truck separately? Okay, so this is exactly where we are coming to a new function, something called a softmax, guys. So what happens is the three people will give us three probability. Probability it's a car is 80. Not a car is 20. Probability of a bike was 60. Not a bike is basically 40. Of a truck was 70. Not a truck is 30. I know. But you can't use this as it is, right? You can't say, hey, this 20% is because of bike and truck, but they have 60 and 70. Rather, what we're going to do is, guys, we are going to normalize this result. That's all. We're basically going to do 80 plus 60 plus 70. The answer is basically what? 210, isn't it? Now I'll go back and say 80 by 210, 60 by 210, and 70 by 210. That's all. What are we going to do? We're going to find the total probability and we'll just sort of normalize it. Now he will tell us, hey, here there is a 30% probability. Here 7, 3, right? Okay. Here it is probably what? 60 by 210, which will be 33% something. It's 210, right? 70, 140, 210, 30. Okay. Here it would have been 63, 18, something. It would have been, oh, it was 1 by 3, right? 33%. So let me go back to R programming. It's much more easier. Okay, so what we're saying is, hey, my individual probabilities are all what? One guy says it's 80, another guy says it's 60, another guy says it's 70. These are the three probabilities. We'll find the sum of probability, which is 210. We'll just divide individual probabilities by this 210, which will give us what? 38% chance that it's a car, 28% chance it's a bike, 33% chance it's a truck right now. So you're basically normalizing it, and now you will say, hey, the chance of it's a bike is basically what? 38%, or say car was 38%, bike was probably what? 28%, and for truck is basically what? 34% here. Now add up the three probabilities, they will sum up to 100. So the softmax is a case where you basically take up the probabilities coming from the individual sigmoid outcomes and you'll basically normalize it. Can you see? We are finding the summation of all the probabilities and we are dividing the individual probabilities by the sum here. So individual probability divided by the sum of probability. This will become what is called a softmax function. So you use a softmax function whenever you want to solve what? Basically a mutually exclusive problem. So he says bike probability was 28 or something, car was 38, truck was 34 something. So mutually exclusive, only one label, I'll say it was a car. At what rate? 38%. At what rate was it a bike? It was 28. What rate was it a truck? 34. Now when I add up, it's 100%. I completely agree with the probabilities. Because sum of probability should be equal to 100, isn't it? That's why, guys, the output coming from a sigmoid, we are basically taking them up and we are normalizing by using a beautiful softmax function that you guys see here. Okay. So sigmoid function is a function you use whenever it's a non-exclusive case. Softmax function is a function that you're going to use whenever it's a mutually exclusive case. So it is only for a classification problem that you need to be worried about this particular point. Are we doing a mutually exclusive classification or are we doing a non-exclusive classification? And one more thing, these are all multi-value outputs, okay? If it was only 1 and 0, one perceptron will do the job. He will tell you what is the probability of respondee, 70. What is not respondee? You can do 1 minus 70, which is 30. For binary problem, you can keep one perceptron, guys, okay? Only for more than 2, you need to start keeping number of perceptrons equal to number of classes. For 2 classes, you can keep 1 perceptron. From 3 classes onwards, you should keep equal to the number of classes. Please keep that particular point in mind. Okay. So if it's a binary problem, it's still single perceptron, guys. Anything more than a binary problem, you should keep number of perceptrons equal to the number of outputs that you want here. And then if it's multi-value output, ask the question, is it mutually exclusive or non-exclusive? If it is mutually exclusive, I use the softmax. If it is non-exclusive, I use the sigmoid. Why? Because in mutually exclusive, I need to give only one output. So I will find who is the max after normalizing, and I will tell that is the probability. While for sigmoid, I will get what? I'll get individual probabilities. I just need to find, whoever is above a particular threshold, all the people will become my outputs. So it is not so exclusive. There can be more than one single prediction is what we are saying. Okay. So these are the 2 types of multi-value output classifications we can do. Mutually exclusive, non-exclusive. It is differed by using a softmax versus a sigmoid function here. Okay. Yes. So do you all agree till here, guys? The architecture, activation functions, how are they set? Are you all okay? I think we've pretty much discussed all the cases. So how does it work for regression? How does it work for classification? How to keep the architecture, how to keep activation functions, we have pretty much discussed them. Do you all agree with it till here? Yes or no? Anu, is it okay? Divya, Nizam, Manjeet, Sanjay, Satendra. Okay. Great. So I think we'll take a small break. Okay. So let's take probably a 15 minutes break. So let's be back at 7:30, and then probably we can move further for another half an hour. Okay. Okay. Thank you, guys.
This conference will now be recorded.
Okay, so let's get started. Okay, so the next thing that we're going to quickly discuss is basically a small example of how do you do a classification model here in Keras. Okay, and then after that we can jump into this digit recognizer case that we have. And I think with that probably we can just call it a day. I don't think we'll have much more enough time to discuss more things. Okay, so let's jump here. So we are importing our necessary default packages in combination: NumPy, Pandas, Matplotlib. The 3 packages we have imported them. So you guys can see here we are making a small data set. Okay. So a data set, there is a function something called makeMoons which will create a data set which will look something like this. Okay? So we have a data set like this. The target is all zeros and ones. There are 2 predictors with us. So you can see there are 2 predictors with us. The target y is basically 0 and 1. which means it's a binary classification problem that we want to. Okay. So what are we doing, guys? We have two predictors, capital X, you can see it is having two columns. There are two predictors. This Y is basically the target. It's having two classes. So we need to go back and create a binary classification model. So what I'm doing is from scikit-learn.model selection, we are importing train test split. We say, hey, capital X is the two predictors. This Y is my target. Split it into X train, X test, Y train and Y test. So what is the proportion? 70-30. So let's hit Control Enter. You can see X train, X test, Y train, Y test has got split successfully. Now we are importing the necessary things like what we did yesterday. From keras.models, let's import the sequential API because we want to add layers in a very sequential fashion. From keras.layers, let's import the dense layer also because we are creating a simple multi-layer perceptron where we'll keep adding perceptrons, one by one. From keras.optimizers, let's import SGD and Adam. So let's hit Control Enter here. Okay, so there's a problem. Why? Because just give me 1 second, guys. Okay. Okay, so we were here. So let me clear all the output. Okay, so we imported the packages. We have created the data set. We have split them into predictors, etc. Right, and then we have split it as train and test also. Now over to the libraries import. We are importing from keras.models something called sequential API so that we can keep adding one layer at a time, one behind another. We are importing the dense layer because we want to create a multi-layer perceptron. Hence, we are importing the dense layer also. Let's hit Control Enter. An optimizer is going to be SGD Adam, about which we'll probably talk in the next class. So we are importing these three things. So it's a TensorFlow backend, Keras. It's importing the necessary packages for us. So what we are doing here is we are saying model is equal to sequential. So it's a sequential API where we are adding how many layers? Can you all tell me? Let me ask you all questions here. So how many layers are we adding here? Look at the code and tell me. Yes, guys. How many layers are we adding here? What is this? I didn't get even a single answer. We are adding a single layer, right? Why? Because we have done only model.add. That's all. Once only we have done. If I do it another time, it's the second layer. I do it another time, it's the third layer we are adding. Do it another time, it's the fourth layer. We are adding only one single layer here, right? Model.add was basically used only once. It's a single layer. How many perceptrons are we keeping in the single layer? Can you all tell me? It's a single perceptron we are keeping, right? You can see here. We are keeping a single perceptron, but we are saying the single perceptron is going to receive two inputs, basically two predictors. So model.add dense of one. So it's a dense layer because it's a multi-layer perceptron. One because we want only a single perceptron there. Input shape is 2, blank. Why is it 2, blank? Because we want two predictors and there's a lot of data points that you're passing. That's why it's a blank. Why did we keep an activation equal to sigmoid? Can you all tell me? Yes, guys, quickly answers. Why is it a sigmoid? Exactly. It's a classification model. You want probability as an output running between 0 and 1. Right? So it's a binary classification problem. We are keeping only one single perceptron. Why? Because it's a binary problem only. So that one probability is enough to compute the other one. I can just do 1 minus p of x. It will give me the other guy. So we are keeping a sigmoid to get probabilities running between 0 and 1. So we are just keeping some, optimizer here. Learning rate is 0.05 something. We are keeping binary cross entropy. Why? Because that's the loss. It's called log loss. Metrics is accuracy, so that you can understand what is accuracy of the model also. While training, he can print both the things. Let's hit Control Enter. Let us look at the summary, model.summary for us. He says what? Hey boss, it's a single layer. The output shape is going to be 1. Why? Because there's only one probability I'll give you. There are 3 parameters I'm estimating. Why? Because there are 2 predictors you have. So weight 1 and weight 2. Then I will have a bias. So that's why 3 parameters I'm going to estimate. So W1 into W2, sorry, W1 into B1, sorry, W1 into X1 plus W2 into X2 plus B, right? So there are 3 parameters we need to estimate. 2 weight values and 1 bias value. That's why there are 3 parameters and all the 3 people has to be trained. Now we are saying, hey, model.fit, this is my X train, this is my Y train. Can you do the feed forward propagate and back propagate, which becomes an epoch 200 times? That is predict and rectify the error. Predict, rectify the error. Predict, rectify the error. Do it 200 times is what we are saying. Let's hit Control Enter. So loss was 0.52. It comes down up to 0.22 and all. Accuracy was what? It was 81%, as you guys can see here. It has climbed up to what? 88% or something. 89, 88 here. Now we will say, hey, for the test data set, can you help me evaluate the model? Sure. He's saying the loss is 0.317 and accuracy was 84%. So the accuracy on the test data set is 84%. Let us create a quick diagram of how the model boundary is working. You guys will be able to see. Since it's a logistic regression model that we have created, where logistic regression models are linear in nature, you can see the decision boundaries are all pretty straight. It's a linear decision boundary he's creating. Logistic regression models are what? Linear models, isn't it? That's why you can see the decision boundaries are all straight. So here he's saying red color portion, you have a 90% of probability of 1, let's say, I'm assuming. Here you're saying 80% of 1, 70% chance you are 1, 40% you are 1, 30% you are 1, 20, 0% you are 1, because you're more of a 0 here. So that's why we are saying 0% that you'll belong to class 1. So this is how the decision boundary is basically got created, because you've created a logistic regression model with a single perceptron, which is otherwise a linear model. It's a shallow model you've created. How can we make it a more deeper model? Any thoughts? How can we make it, sorry, not a deeper, but more of a non-linear model? How do you think we can probably make it as a non-linear model? Any thoughts? So now we've created a logistic regression, right? We see that logistic regressions are linear in nature. That's why decision boundaries are all pretty linear. What do you guys think we can probably do here to make it probably a non-linear model? Any thoughts? Change activation function. Okay. Change it to what? Change the activation function to what? Let us assume there is something. Okay, let's say ReLU. ReLU we know is a non-linear thing. But do you think this is right? Changing the activation function here, do you think it is right? How many of you are saying yes, you need to change the activation function here? How many of you are saying no, you should not change the activation function here? Just because I'm asking a question, don't go with the answer no. It could be yes also. Just tell me yes or no. Why do you say so? Neural networks is basically a concept where there are a lot of small details, guys. So you need to pay attention to the details. That's why I'm asking you guys a lot of questions here. Okay, so tell me. So if I were to make this as ReLU, thinking that ReLU is a nonlinear function, I'll make my model to be nonlinear. Do you think we are right in making it as ReLU here in place of the sigmoid that we had previously? What are your answers? Yes or no? Why do you say yes? Why do you say it's a no? Let's take a guess. It's completely okay to give wrong answers. Just think, participate. What do you think? Yes or no? If it's a no, why? If it's a yes, why? Yes, Nizam, what do you think? Anu, what do you think? Jishbu, Manjeet, Manohar, Sanjay, what do you guys think? And sorry, it's Jishbu or Jishu? Hope I'm pronouncing your name right. Jishu, is it? Collier's Joy. Okay. What do you guys think? Not needed. Already activation function makes it nonlinear. The sigmoid is more linear still, I would say. Only towards the end, he's kind of taking a small cutoff. I would still say it's kind of linear. In ideal world, it's not linear, but yeah, still it's linear. I think Yatendra has an answer. So, okay. So changing the activation function at the last layer is not the right thing to do, guys. Why? Because the last layer is going to decide what kind of an output you want, correct? Even other layers you can do it, but the last layer you can't play with, this guy. You can't keep it as ReLU. What will happen? I'll start getting probabilities from 0 till infinity. I'll get 1.7, 170% probability. That's not right, isn't it? So last layer activation function cannot be changed. But Nizam, your answer was right. Changing the activation functions will make it non-linear, but not the last guy. The last layer is very important, guys. Let's please keep that thing in mind. The number of perceptrons are equal to the number of outputs, and the activation is decided by the type of output you want. It's not about the nature of the model you want. So I can't touch this guy. I need to keep him as sigmoid. I can't make him as ReLU, even though what you said was perfectly right. I need to change the activation to make it non-linear, but surely not the last guy. He's an exception. Now tell me, guys, how do you think I can make it as a non-linear model? I think it's a simple answer. Why do you think you can make it as non-linear? How do you think you can make it as non-linear? Perfect. Very good answer, Yatendra. I just have to go back and add new layers, guys. That's all. So I'll just say, copy and I will paste him here. So he will be my last layer, obviously. He will have an activation of sigmoid, but this first layer, I can probably make it as ReLU or something. I'll just hit Control Enter. This is the model summary. So you can see this is a dense layer. We have like one single perceptron. There are 3 parameters he's estimating. Why? Because there are 2 features with you. So 2 weights you need, W1, W2, and a single bias you need, hence 3 parameters. The output coming from the first layer will be of shape 1, which will get connected to the next layer. So only 1 weight is required and only 1 bias is required. That's why 2 parameters are needed here to train. Let's go back and train this particular model. Okay, so the loss and all has come down. We can just go back and evaluate it. You're getting 0.318 and 84% accuracy. I don't think it still would have become nonlinear, but still, let's guess. It has become occasionally nonlinear. It's not a straight line, but at least it has got little curve here and all, right? So what you need to do is you need to add more perceptrons. I'll add 5 perceptrons right now. You can go back and see. So we have 2 features as inputs. There are 5 perceptrons. So 5 into 2, 10 weights are required. And what is happening? Since there are 5 perceptrons, 5 biases are required. Hence, there are 15 biases here. Okay. So what do we have? We have 2 features. We have 5 perceptrons, right? So they will all get connected here. So what's going to happen? 5 into 2, 15 connections is basically what we're going to have. Sorry, 5 into 2, 10 connections is what we will have. And 5 weights is what we will have here, isn't it? So that's why 15 parameters you will have. And this layer is going to receive 5 inputs from the previous layer. And only 1 single perceptrons are here. So 5 connections, 5 weights are required, and 1 perceptron only, 1 bias is required. So 5 plus 1, 6 parameters are here. Let's go back and train the model right now. Let's just come down here. We'll predict the results. We'll ask for the accuracy. Now we'll go back and create a decision boundary. You can see it's nonlinear, right? It's going like this, then it becomes nonlinear like this. I think it's trying to imitate how a ReLU will work. Do you see it? So till 0, it is what? I think it's kept flat lump, something like this. From 0 onwards, it's doing something, right? So it's working almost like how a ReLU will work, right? So all you need to do is you need to go back and add many layers, guys. That's all, and many perceptrons. Look at this case here. Okay, this case. So I'm adding 1 layer with 4 perceptrons, another layer with 2 perceptrons, last layer with 1 perceptron only, because I need a single output probability in sigmoid. Atom, binary cross entropy, accuracy. Let's hit Control Enter. Fit. Let's go back, evaluate. Let's ask for the accuracies and all. Plot the decision boundary. Now you can see this is exactly how the model has created its decision boundary. Saying, hey, I'll create a boundary like this, where I will say anybody above the boundary is blue, it's all zeros. Anybody below the boundary is all red, which is all ones. So this is how he was able to create the boundary for us. So here what we have is a more non-linear boundary. Previously what we had was more of a linear boundary. So I'll just go back and create this again. I'll leave it there. Plot. Okay, so this was a very linear boundary that we have, but here we are getting a much more non-linear boundary because we've added many layers, many perceptrons with different functions. So we added ReLU here, we added another ReLU, we added a sigmoid here. Okay, so this is basically your deep learning model that you've created, a multi-layer perceptron with many layers and many perceptrons, which makes your model more non-linear in nature. That's why you can see the boundary is more non-linear in nature here. So now look at this data set. I want you all to help me create the model. Okay, so we are importing the iris data set. So I have a species column, Setosa, versicolor, virginica. There are 3 outcomes that are possible. Now I'm just going to go back and create all the dictionaries and all. So what we are doing is, guys, we are taking up the target, Setosa, versicolor, virginica. These are the 3 outcomes. The 3 outcomes cannot be used as strings. You need to convert them as numbers. So we are creating a dictionary where it will say, hey, in place of Setosa, I'll use it as 0. In place of versicolor, I'll use it as 1. In place of virginica, I'll use it as 2. And tomorrow when you predict it as 0, I will understand it's a Setosa. When you predict it's a 1, I'll understand it's versicolor. When you predict it's 2, I'll understand it's virginica. So we are converting those species column, which is string, right now into numbers. Now what we need to do is, guys, this is a very important step. You have to basically do something called as one hot encoding here. Okay, it's a very common practice. It's actually done in many multi-class classification models. You'll basically do something called one hot encoding. What is a one hot encoding? Very simple. So say for an example, you have a target column with you. Okay, suppose say you have a target column with you. The first sample says, hey, I'm a Setosa. Second sample is also saying I'm Setosa. Third guy says I'm versicolor. Fourth guy says I'm virginica. The fifth guy says I'm versicolor. All you're doing is you're saying one column for Setosa, one column for virginica, one column for versicolor. Since he is Setosa, it'll be 1, 0, 0. Setosa 1, 0, 0. Virginica 0, 1, 0. This is also virginica, let's say 0. Sorry, it is versicolor, right? 0, 1, 0. This will be 0, 0, 1, and he will be 0, 1, 0 because he is versicolor. Okay, VER, VER. So if it's versicolor, it will take 1. Other cases, it will take 0. Virginica, there alone will take 1. Other cases, it will be 0. So a single target column is now converted as 3 target columns. This is what we call as one hot encoding. In your Keras, there is a function which will easily do it for you. So from keras.utils.nputils, you're importing a function called to_categorical. And now you will say, hey, take up this y column, okay? I've made it as 0, 1, and 2. I don't want it as a single column. I want it as 3 columns. One column for 0, one column for 1, another column for 2. So you're saying convert it as 3 categorical columns. This is how the 3 categorical columns are going to look like. So the first samples, they are all for what? Setosa till here. Then the next few samples are all for versicolor till here. Then they are all for virginica till the last. Now we will go back and create our train and test data. Now tell me guys, we are saying model is equal to sequential. I've added a single layer only. How many perceptrons are we having in this model? Can you all tell me? Looking at the code, how many perceptrons do we have? Why do I have 3 perceptrons here? Why did I not have 4 or 5 or 6? I could have kept 10, right? But why did I keep 3? 3 inputs? No, there are no 3 inputs, there are 4 inputs. Petal length, petal width, sepal length, and sepal width. There are 4 inputs. So input shape is 4 comma blank. Why? Because there are 4 predictors. Petal length, petal width, sepal length, and sepal width. There are 4 predictors, not 3 predictors. So why did I keep 3 perceptrons? So this is my last layer, isn't it, guys? Last layer should basically happen. How many perceptrons? It should have the number of perceptrons which is equal to the number of outputs, isn't it? How many outputs are we having? We are having 3 outputs. That is why 3 perceptrons here. Right? So what is this layer actually? It is the last layer for us. Last layer should have how many perceptrons? It should basically have the number of perceptrons equal to the number of classes. How many classes are we having? We are having 3 classes. That's why 3 perceptrons here. Input shape is 4 comma blank. Why? Because we have 4 predictors: sepal length, sepal width, petal length, petal width. So why do you think I've kept activation as sigmoid? Why did I not keep it as ReLU or something? Why is it sigmoid here? Why is the activation sigmoid? Good answer, Sanjay. Yes. And Sanjay, Manohar, did you guys realize why we kept 3 in the previous case? It's not number of predictors. So you guys gave me an answer saying it was number of predictors. No, it's because of number of outputs. Sanjay and Manohar, is it okay? Okay, cool. Okay. So why are we keeping sigmoid? Because if all of you told me that we are looking at classification, so we need probability. So why did I not keep it as softmax? Why do you think I kept it as sigmoid? Because sigmoid and softmax, both of them go for probability models. Why did I keep it as sigmoid? Exactly. We want what? We want a non-exclusive case. Sigmoid because all 3 people will give their own probabilities. One guy will tell you how much of setosa, how much of versicolor, how much of virginica. All the 3 people will give you the 3 outputs. So you just have to keep a benchmark and fetch how many other labels you want. You can fetch 1 label, 2 label, 3 labels, any number of labels you want. So we are keeping sigmoid because it's a non-exclusive problem. So that particular row could have been setosa as well as a versicolor as well as a virginica. We don't know. We are just saying it's a non-exclusive problem, but ideally it's not a non-exclusive problem. It's a mutually exclusive problem. I should have made it as softmax, which we'll make it in a minute. So now we'll keep it as sigmoid. We'll hit Control Enter. We'll ask the model to predict. We'll ask for probabilities right now. I'll make it as 100. Okay. Now you can see. So this guy is having how much of probability? 57.69% probability for being versicolor and 54.7% probability of being virginica. 55 plus 55, 110% probability. Surely it's not less than 100. Ideally it should have been less than 100, right? Why it's not so? Because it's not normalized. Every neuron will tell you, hey, this is 0 versus 100. This is 57 versus 43. This is 54 versus 46. So everybody is an individual logistic regression model. These guys will make sure that they don't go above 100. The total need not be equal to 100 because it's a what? Sigmoid problem. So now you will ask, okay, so he is saying there is a chance of it being a versicolor as well as a virginica. So you'll say this flower is both a versicolor and a virginica. You'll say it's a hybrid. Look at this case. He's saying 0.8% probability. He's saying 42% probability, 21% probability. Surely it's not adding up to 100. It's less than 100, far less than 100. But since you keep threshold like above 50 or something, you're saying it's only a versicolor. But much more easier it could have been if it were a mutually exclusive problem. We could have kept it as softmax. Let's hit Control Enter. Let's go back and ask for the probabilities. Now you guys can see that the probabilities will add up to 100. Here he's saying it is 81.8%. Here it is 17.7%. Here it is 0.3%. Actually, if you add it up, it will be 100. Here it is 41.10, 53.78. Here it is what? 5.10. When you add up, it will be 100. So when I keep softmax, it's a exclusive case, which means only one label can be fetched. I need to find who's the max out of these guys. That will become my final label. That's all. So I just need to go back and ask, hey, who's the highest? Can you tell me? Then based on that, we'll go back and ask for the final classes. That's all. Okay. Here I should just go back and say dot map using the inverse dictionary. Target dictionary of inverse. Okay. So NumPy array doesn't have map. So don't worry, I'll make you a series. That's all. So now what will happen is instead of having the 0, 1 and 2 as numbers, you're finally making it as individual classifications. That's all. Okay. So this is exactly how you differentiate between a mutually exclusive and a non-exclusive case. It all depends on the function you're keeping. Please understand the last layer, guys. It's pretty important. So the number of perceptrons is equal to the number of classifications or the number of probabilities you want. Input shape is the number of predictors. You make it more and more non-linear by adding more layers, more perceptrons. Activation function can be sigmoid, softmax, depending upon whether it's a non-exclusive versus a mutually exclusive case you're solving. Okay. And I think this is pretty much it about multi-layer perceptrons for a classification and regression problem. So how is he solving it? That's a study that we need to probably do, which we can take it up in the next class. Okay. So till now we have basically solved two of the points that we wanted. Number one was architecture. We have understood in and out how to design the architecture of a multi-layer perceptron model. And over to number two, we have also discussed about how should I design my activation function. So both the points are very, very important. And now for different use cases, you guys right now know how to solve them or how to design them. So designing a multi-layer perceptron is something I'm pretty sure everybody should be able to do it by the end of today's class. So how are they getting trained? The max behind it, everything is a training algorithm, which we'll probably take it up in the next class. Okay. Yes. Till here, are you guys convinced with all the things that we've discussed? Yes or no? How to design a multi-layer perceptron models? What is the feed-forward propagate math behind it? Does everybody agree with me? So by the end of the day, everybody should be an AI specialist. You should be able to design your MLP models. Yep. Okay, awesome. So thank you guys. Thanks for joining. I know it was a pretty exhaustive 3 hours, too much of information. Thanks for being so patient, listening to this. Okay. Thank you guys. So what I'll do is I'll upload, and once again, only before the class it strikes my mind that I should be uploading this particular OneNote. I'm sorry, I'll make it a point that I'll upload all the OneNotes that we had till now. Okay, luckily, we are maintaining it pretty good also here. So I'll upload everything by today night or tomorrow afternoon, earliest possible. Okay. Thank you. Thanks all. Let's catch up in the next class. Thank you guys. Thank you, Anu. Thank you. Yes, Sanjay, I'll pass on the information on how to install it. It'll be a PPT and an environment file. I'll upload it. Thank you guys. Bye.